Okay. Anyway, another GADEPs day. It is much easier to organize just one-day activity. It's much cheaper to organize this kind of things instead of 1 week activity. But okay, so let me start with what I want to say. Okay. Well, a month ago when I was in China, I started this project with Jin Chao and Mohammed Elmi. The project is still under construction, but I will give a report of what we are going to do. So first of all, we start from a perfect field. Of characteristic P. So what is the perfect field? The perfect field is the field such that K, the morphism, the Frobenius morphism, is isomorphism. And A to the P in a field of characteristic P is a morphism of groups. For example, but if you don't want to annoy yourself with this generality, for example, you can take K, a finite field of characteristic P, and you see that A going to the A to the P is actually the identity in this field, and so it is automatically isomorphism. So before some X, a smooth projective variety over K, and since my elliptic curve students are here, you can take, for example, the elliptic curve, for example, actually I'll take this one, T2 x minus T3. Then the discriminant must be, let's say, 27 to T3 to the 2 minus T2 to the 3 not equal to 0. This characteristic, maybe let's just a characteristic. In this case, I will take characteristic not equal to 2 and 3. I mean, for example, this is this example. I will do some computation. Okay, so we are considering algebraic geometry of our finite field. So another notion that I needed, Cartier operator. The only thing that I will tell, I will not completely define the Cartier operator, but let me just say what is its properties. Cartier operator, so here I will a little bit need the language of sheaves. This is the sheaf of differential forms on X. Differential I forms. I will need differential I forms such that are closed. And the Cartier operator to each closed differential forms associate another differential form. Anyway, first of all, it is an operation on differential form. It makes sense only in characteristic P. Over complex number, that doesn't make sense. And I will tell its properties. And in a minute, I will be back to the elliptic curve case, and then it will get elementary. But let me just, those who knows the notion of differential form on varieties. So it has this kind of, so C, if you take a function on x to the power p and multiply it with some differential form. So this is the differential I form, and this is a function. So the first property that f to the b always comes out of the operator and becomes f. It's a kind of linear, but if the coefficient is f to the p, so f is a holomorphic function. It's a holomorphic function. Well, we are in character p. It's a regular function on x, omega differential R form, and Cartier operator of exact differential forms. So if the differential form is exact, it's Cartier operator. There it is 0. The Cartier operator. Another thing is this one, fp minus 1 df for f o x. So if you have a regular function on your variety, and you have fp minus 1 df, in characteristic p, this is not exact. But let me write. If you are in characteristic 0, this is exact because this is df to the p to the p. But in characteristic p, well, you have divided by p, so this means that you have divided by 0. But so this is in characteristic this is exact only in characteristic 0. But in characteristic p, it is not 0. And Cartier operator actually, so you cannot say that C of this guy is 0 because this is not exact. And actually, I have made a mistake here. And actually, here, it is, just a moment, I have made a mistake here. Yeah, exactly. It is df. Okay. So you see that it is whatever it is, it's a operation purely in characteristic p, and of course it will respect the wedge product, alpha omega, say alpha, say omega, and the alpha omega. Alpha, for example, is I form, and omega is a G form. Anyway, the statement is that there is a unique operator on closed differential which associate to any closed differential form. An arbitrary differential form, it satisfies these properties, and actually it is unique with these properties. So there is just one operator with these properties, and that's unique. So this one I will not prove it, but anyway, just to have a feeling of what kind of operator is this one. And as I said, this operator doesn't exist if you are over complex number, characteristic 0, etc., etc. Okay, so I will need this operator, even I didn't prove that it exists or the uniqueness with these 4 properties. But the idea is that if for example, in the case of elliptic curve, if you know these properties, you can play and you can compute the whatever you want. Okay, so let's go to the Calabi-Yau. Calabi-Yau n-fold Okay, whatever is definition of Calabi-Yau n-fold, I will need just one consequence of this Calabi-Yau-ness, and this is that there is a unique up to constant up to multiplication by a constant, there is a unique regular n-form on X. Unique global. In a way, you have to know a little bit language of algebraic geometry, but maybe let's say the case of Calabi-Yau one-fold, and it is easy to prove that in this case the Calabi-Yau n one-folds, they are just elliptic curves, and then for example if you take this, and actually if the characteristic is not 2 and 3, then you can write any elliptic curve in this format. And in this case, there is a unique one form, let's call it alpha. And in this case, alpha is dx over y. So it doesn't matter what are the other conditions of the being Calabi-Yau. I not just need that this x. So first of all, dimension x is n, and there is up to constant, there is just a unique n form on this one, and in the case of elliptic curve is this one form is dx over y. Okay, so now let's go to the Hasse-Witt invariant. So the point is that you have and this one is independent of the characteristic. So this means that at the end we have the Cartier operator. Let me say. We have a n form on it. And this is the and you apply the Cartier operator on this alpha. But what you obtain, it is also, well, first of all, there is this n form is automatically closed because the varieties of dimension n, on a variety of dimension n, there is no n plus 1 algebraic n plus 1 form. On the elliptic curve, you don't have two forms, so automatically d alpha is equal to 0. So, but the point is that this is again a global n form on your variety, but I am in the Calabi-Yau context. This global n form, there is just one global n form up to. So this must be some multiple of alpha itself, and actually this constant is the Hasse-Witt invariant. So let's say Hasse-Witt invariant is just this constant that let's call it x alpha. And for some reason, since my field is perfect, a going to the a to the p as isomorphism, this means that I have the inverse map. And so I will take the Hasse-Witt invariant is defined by p square root of this constant. So this is the definition of Hasse-Witt invariant if you know the Cartier operator. But as I said, if given any variety with these 4 rules, you can always try to compute this. You can always compute this number. Okay, so let's back to the case of elliptic curve case again, because the idea is that we want to generalize things to the. In the case of elliptic curve, And in particular, in this framework, so in the case of elliptic curve, let's call this one E, not X. What you can prove the Hasse-Witt invariant of E with this differential form. And if you want, let's call this one T2, T3. Anyway, it is not difficult to prove, but one can check that this is even you can consider as a function of t and 3 is a homogeneous polynomial of degree p minus 1. P is the prime in fp t2, t3, but homogeneous in the sense of taking away, considering the weight 4 and the t3. Anyway, actually, if for the first time you see the Cartier operator, computing the Hasse-Witt invariant, in this case, is a very easy exercise. I mean, this is a very, I think maybe it goes back to Hasse itself 100 years ago. So it is, one can take the rules and really start computing the Hasse-Witt invariant easily. So this statement is not hard, but the main reason why this Hasse-Witt invariant appeared because if you take, for example, T2, T3 in a finite field, I mean, instead of arbitrary perfect field, take a finite field, actually this is P plus 1, the number of FP points. So you just take this elliptic curve and you count the number of FP points. FP is finite, you can make this count, and P plus 1 minus. And for some reason, which has to do with Hasse bound, this P is equal to 0, but you keep this P there also. Traditionally, the people, they write it because there is some Hasse bound. But maybe the main reason for considering Hasse-Witt invariant, Hasse-Witt invariant are basically responsible for counting FP points of varieties. And okay, and if you look the Wikipedia of Hasse-Witt invariant for elliptic curve, you will find more than 10 equivalent definitions. And I want to take, okay, so the main goal is actually computing Hasse-Witt through modular forms. And this one that I want to generalize to Calabi-Yau varieties. So at the end of the day, Hasse-Witt invariant for Calabi-Yau varieties is defined. This is the only definition that we have. What I want to do, let's say there are more than 10 equivalent definitions. One of them has to do with the modular form. I want to take the definitions through modular form and try to generalize it to Calabi-Yau context. This is the whole goal that I want to take in my mind. I told my student that in the first 10 minutes there will appear modular forms, but actually in the first 20 minutes, sorry. Okay, so let's go. In the last 2 weeks I was teaching modular forms, so there is Eisenstein series. So let me write it. 1 minus 2k b k sigma k minus 1 n n equals to 1 infinity q. Let's just take as a function in q to the n. This is Bernoulli number, and this guy is sigma in is some divisors of n to the I. I mean, these are Eisenstein series. They are modular form only for 4, 6, 8, even bigger than 4. And something that I just announced in my course, but I didn't prove is that ek, all of these ek's at the end can be written as a polynomial in E4, E6, polynomial of homogeneous polynomial of degree k in the but again homogeneous considering degree of E4 4, degree of E6 6. Anyway, all these EKs are modular forms, or whatever is the definition, but at the end you can write all EKs in terms of polynomials E4, E6. For example, at the end is the E8 is E4 to the 2, etc., etc. E10 is E6, E4. I mean, this is a kind of classical things that one does in the framework of modular forms. So you see that at the end of the day, you see that there is. I was claiming something purely characteristic P, and then there is some polynomial there, some polynomial there. And so let's the EP minus 1 is a polynomial. I will call it A because the people around 1970, like Swinert and Dyer, they called it A. You can write it in terms of E4, polynomial in terms of E4, E6. And for some reason, because I want geometric reason, maybe I put the coefficients 1/12 minus 216. But anyway, the polynomiality will not change. So, and then the degree of this polynomial is P minus 1. You see that at the end there is some similar, some polynomial of the same degree popping up. And actually, the second definition of Hasse-Witt invariant is exactly through this one. This is the lean. No, this is our rational number. This is for the rational number. So this means what the link cuts are 1970s, 1973. Okay, first of all, this is a polynomial with rational coefficients. In principle, the denominator of coefficient might be P. It might happen that it doesn't make sense to talk about mod P of this guy. But the one statement is that the prime number P will not appear in the denominator of the coefficients of A. So this means that you can take mod P of the coefficients of A and then A itself. So A So from now on, I will take mod P. So mod P, this guy is exactly the Hasse-Witt invariant. And so you can compute also the Hasse-Witt invariant through modular forms in the sense that you write EP minus 1 as a polynomial E4, E6, put this coefficient, take mod P, and then, and of course, there was what I said, if at the end mod P, if T2, T3 are in FFP, this is the same as P plus 1. Anyway, we have three different quantities. One has to do with f point p point content. This one has to do with Cartier operator, and this one has to do with you get it through modular forms. At the end, all these three quantities are the same. This is a kind of classic. This is a kind of classical, but the thing that I want to focus is that this Hasse-Witt invariant is computed through modular forms, Eisenstein series in this way. And this is the goal of the talk is that this feature of the Hasse-Witt invariant can be generalized to Calabi-Yau varieties. Exactly. So now this is a polynomial in two variables, and then just substitute it T2 and T3 there. Okay. So okay, let's. Okay, so the goal is generalization of this one to Calabi-Yau n-folds. Well, actually, there is two issues. The first of all, what is the theory of Calabi-Yau modular? What is the theory of modular form in the Calabi-Yau varieties? What are the corresponding Eisenstein series, etc., etc. But I will try to explain all these. Okay, now I started with Calabi-Yau varieties, so if you don't understand, you are free. Okay, so let me, first of all, it has to do with the curve. Maybe. So the point is that this first of all, you have to say that what is T2 and T3? I mean, at the end of the day, T2 and T3 at some point they will replace with E4, E6, etc. And okay, maybe before. Let me first write the general context. So the point is that in order to see that what is exactly the T2, T3, you have to consider this moduli space. Moduli space of X alpha X Calabi-Yau n-fold alpha this regular n form. And in some sense, you enhance your Calabi-Yau variety with that one. In order to okay, so On this moduli space, there is this GM acting. Let me rewrite it. Maybe I've just, again, there are schemes going on, but I will take GD. So if K is your base field, then the multiplicative group of this guy acts on S. What is the action? X alpha is X, just multiplying alpha with A. I will take A minus 1. And then A in GM, X alpha in S. And well, one of the big
X is a family or?
huh?
X is a family?
No, it's not. It's just one variety. But and then consider the all such things. And actually, I have to say, X a Calabi-Yau n-fold in a component of a Hilbert scheme, etc., etc. But I am doing a little bit intuitionally. No, alpha is regular differential n form on X. Alpha is regular, no. But anyway, again, I will tell you. The point is still I don't know. Kanja has a natural scheme, structure over some 1n for some n, and we have a universal family over it. Okay, whatever I am saying, we have a moduli space problem. In the algebraic geometry, when you have a moduli problem, you have to start constructing your moduli space, etc., etc. And nowadays, I will use the CM instruction. But in the case of elliptic curve, then basically this is this one. S is a spec Z 1/6, because at the end the 2 and 3 are not good for this purpose. T2, taking T2, T3 as a variable, and then you inverting the discriminant, 27 to T3 to the 2, T2 to the 3. This is some affine variety, and actually you have universal family over this one. And the fiber, if you take any geometric fiber, point here, this is the fiber of this one is just your elliptic curve. And of course, this is the moduli space together of X with differential form. So this means that at the end you have to say that your differential form. So the moral of the story is that this is not just arbitrary two-parameter family of elliptic curve. This two-parameter family, the two parameters, they have moduli space interpretation, and actually this two-parameter family is the universal family over your space. And usually, for example, in physics, people they just take the two-parameter family, three-parameter family. They don't they start doing computation. But in this case, what I'm saying that it is it has this. So the point is that we have to solve the same problem in the case of Calabi-Yau varieties. We have to sit down. Look the results in the case of Calabi-Yau n-fold, what are known about the moduli space, make addition with this regular differential form, construct similar families either in explicit equation, or if you are abstract algebraic geometer, try to to say that this moduli space exists, universal family exists, etc., etc. So before going to generalize this thing, then we have to solve this issue of the constructing moduli space. And actually, I mean, constructing moduli space in algebraic geometry is a difficult issue. But assuming that this is done, for example, in the case of mirror quintic, maybe this one I didn't. Okay, maybe let's say. There was one example which is actually in the article, at least 4 examples we can take. There is an example of Calabi-Yau variety called mirror quintic, and at the end of the day, maybe this one exactly I have to write. So the mirror quintic originally it is this family. Well, I will not take the quotients. X2, well, let's just x1, x2, x3, x4, 5. So there are these just monomials popping up. Now, in a minute, I will put the parameters. So this one inside P4. It doesn't matter the coefficient. But after actually this, when a little bit you worked out, you see that there must be this maybe I put this parameter T1. This 2-parameter family. And then you can fix alpha, etc. What I am saying that in this 2-parameter family of quintics, it has a moduli space. It has a moduli space interpretation in terms of certain Calabi-Yau varieties. But for now, you can. It is not just a random 2-parameter family. And
but this is not the whole moduli space in the case of Calabi-Yau 3.
No, okay. This is either you have to consider the quotient of this one by automorphism, or say that this is the moduli space of quintics with certain discrete group acting on it. But anyway, there is, well, at the end of the day, there is some moduli space interpretation, but this was this 2-parameter family.
You can just restrict to that.
Huh?
You can just restrict to that slice in the parameter space. You can just take that.
No, but if you have the moduli space, any moduli space, you take some subspace.
Yeah,
Not necessarily there is a moduli space interpretation for this subspace.
that's correct.
What I am saying, for this slice, there is moduli space interpretation, putting the fact that this automorphism, this is the take the automorphism groups of this one. This is a discrete group. These are the only quintics with such automorphism groups. And then this means that the moduli space, you have also some discrete group acting on quintics, etc. Or you do like in physics. You take the quotient, the singularize, and then they say that we have a Hodge Calabi-Yau variety of type 1, 1, 1, 1, etc., etc. Huh? No. For the moment, this is just putting the. And at the end of the day, in this case, what I've said, this S will be a spec. I didn't tell. 1, 5. T1, T5. And then the discriminant will be something, just a moment, T5, and then T5 minus T1 to the 5. So anyway, this family of varieties over these things has a moduli space integral. This is a moduli space of something I didn't write, and actually this is the universal family over this one. Okay, maybe just 20 minutes. So, okay, maybe just to again. So first of all, once you do this one, well, I have to say that what are Calabi-Yau modular forms. And okay, this is independent of this. So in a moment, I will be back to this moduli space thing. Let me write it in. Here I need this hn minus 1, h1. So in physics, the people always take families of Calabi-Yau varieties. 0 is the mum point. Whatever this is the definition of the mum point, at the end of the day, one consequence of the mum point is that you will have cycles delta 0 z in hn and delta I z I equal to 1, 2 until m in hn x z z. And there you have this m plus 1 cycles, and whatever condition you have, this under so monodromy around zi equals 0. It has a delta iz. Always go to delta iz plus delta 0 z. And delta 0 z is the fixed. And maybe, so if you take the differential form, the people take arbitrary differential form over a regular differential over z. And maybe the only thing that you must know that alpha, this holomorphic period, holomorphic at z equal to 0, and because of this thing, alpha z delta iz is ln z 2 pi I. This guy plus something holomorphic. Anyway, now we start. We are going to some context in physics. The people start computing. They take families of Calabi-Yau varieties. They find this mum point, and what I need is actually this z1 mirror map z2 with m going to q1 q2. So these are the generalization of this q that we saw in this modular form case. Qm, and what is q? Q is exponential 2 pi I alpha z delta 0 z alpha z integrated over delta I c. And it turns out that this is the biholomorphism. Actually, it also follows from the definition of the. And so this means that you can invert this map and consider z1 as a function of let's say this q. So these are all multivariables: z1q, z2q, zmq. So this is the whole business of the people in physics. They structurally they do a lot. They find this one. They define the mirror map inverted. I don't want to get too much involved in this one. So, okay, so I wanted to say the generalization. So actually, the natural scheme, affine scheme structure. Let me maybe complete this one. The affine scheme structure. So this means that S is a spec of some. Okay, we have to invert some numbers. So for always some prime numbers are bad. We have to throw away. In the quintic, the 5 is bad. In the case of elliptic curve, 2 and 3 are bad, etc. And then this means that there will be, we can write it as algebra on many parameters. And maybe we invert something, but at the end, this one, then divided by some ideal. So the S always will be some polynomial algebra divided by some ideal. And if there might be some discriminant, but the discriminant also you can insert it here, because if there is something like this, then you just introduce another new variable, let's call the ts plus 1, and then 1 is equal to ts plus 1 delta, and you put it in the definition of the ideal. So for this reason, I don't write it. But anyway, but the one part of the conjecture is that this coordinates has some good properties with respect to CM action. So this may, maybe one conjecture ti. Let's say ti x a minus 1 alpha. So these ti's are function on this moduli space. So this can be considered as function on x and alpha. So you can evaluate ti over x alpha. And there will be this functional equation popping up. For some ki integers. So our algebraic geometry part is moduli space contracts a little bit finer. First of all, the moduli space is this, it is affine. Moreover, we can choose coordinates on this affine moduli space such that these coordinates, they have the simple functional equation with respect to the CM action. So there are a lot of works one has to. I don't know if for arbitrary Calabi-Yau n-fold one can prove this kind of statement, but for examples it is not hard. For example, in this quintic one can do it. In the case of elliptical one can do it, and at least for more. For examples, one can do it, but I don't know if in general one can prove this kind of statement. Okay, so let's go to the goal. So at the end of the day, these ti's are algebraic incarnation of this T2 and T3 or Eisenstein series E4 and E6. Once you do this job, and then. Conjecture 1. By the way, I am writing the conjecture, but the result of the article is that these conjectures are true in many interesting examples, many interesting examples of Calabi-Yau varieties. So it is not. Okay. So maybe I write this one and then. Exactly, this is the KI to the weight. In the case of this elliptic curve, one of the 4 it would run 6. But for example, in this case, this one will be, this will be the 5, this will be the 5, this will be the 1, etc. But anyway, I think if you digest the things in the case of elliptic curve, that's already good. Okay, so first of all, these TIs. My theory of algebraic modular forms. But modular forms are useful if you do Q expansions, okay? And maybe I don't know. Okay, I said this is not part. So this is my moduli space context, and this was the context that the physics they take it, arbitrary families of Calabi-Yau varieties. So the idea is that, okay, I want now a dictionary to transform these algebraic TIs into some Q expansions. So one has a precise dictionary, to each ti, one associates some aiz. So now from this side, I want to go to this side. aiz, in a minute, rational functions in Z. And remember that Z is Z1, Z2, Zn. And once you do this one, you have also this. So this is a rational function. You take this holomorphic period. So this one I didn't say how to do it, but always you can arrange for rational functions such that once you multiply it with holomorphic period, make it to the p minus 1. So this becomes a holomorphic function in Z, and actually rational function well defined. Holomorphic at 0. In my examples, most of the time they are just a polynomial function. But this is a holomorphic function in Z. Now you insert the mirror map here. So this is so what I'm saying that now you insert the mirror map here, and then you get inserting mirror map, and you get let's say some formal power series in Q.
What is this b? B minus 1?
What?
What is the exponent b minus 1? What is b?
The p is the prime. It is now it is now purely complex. Now I want to go to something, produce something in characteristic p.
Okay.
So now I have fixed p. It must be not. So I have to say at the end I will always work with p, not dividing this n. Example we know what is n. And what I'm saying that there is a precise dictionary to each ti associate a q series. Okay. So let me try to go to one. Okay, this one I told it. Okay. So okay, so there is anyway. This those who doesn't know these things, one has to write it down clearly. I have to say what is this procedure associated to EI, this rational function, etc. But so first of all, after taking after some multiplication, it's that this becomes formal power series in Q. And actually, this is conjectural. You can verify it 1,000 coefficients, whatever. But no, exactly. You have it has to do with the choosing the mirror map, because the choosing the mirror maps you have to you have some multiplication by constant involved.
Can you recover this Q expansion somehow using the Gauss-Mann?
Yeah, we did it. Well, but for this Gauss-Mann issue, one has to go to this bigger moduli space. For the moment, I am this smaller moduli space, which in the case of elliptic curve dimension 2. But for the Gauss-Mann equation, it's better to go to the 3-dimensional. But anyway, what I am saying, for example, this fact that whenever you insert the mirror, for example, the mirror map itself, it has integer coefficient. This is taking, let's say, up to the gain multiplication, multiplying Q with some constant. It had integer coefficient. It is conjecture, etc. But all these conjectures, we don't care, because in practice, when we put in the computer, compute the first 100 coefficient, 200 coefficient, they are already integers. And then we say that it is OK. Right? The point is that you can do mod p. So this means that you can do mod mod p of these guys. And the point is that again, well, I am writing conjectures, but the results are that these conjectures are valid for many primes, for truncation 200, etc., etc. No? So these are not just random. Huh? Well, exactly. And actually, Muhammad is supposed to verify for more. So there is a unique polynomial. In this T1, T2, Ts, degree, of course, that again, degree Ti, I have to, of degree p minus 1. And actually, I have to say, because there was some ideal involved, I mean, uniqueness up to that ideal. Anyway, let's just the unique polynomial degree p minus 1 such that a T1Q. Yeah, this one actually, by the way, in the case of elliptic curves, I forgot to write that the EP minus 1, when you take mod P of coefficient, it is 1, actually, and then there was, actually, I will use this one. But anyway, I'm trying to say that what is the Hasse-Witt invariant. So if you take this things modulo P, there will be a unique polynomial relation of constant. So you have this, and actually in all the examples it is 1, but I don't know if I have to put 1 or any arbitrary constant. So there is a unique polynomial relation between T1, Ts, considering modulo P. And actually this A, T1, T2, Ts is exactly the Hasse-Witt invariant of this D moduli space. So this means that T1, that is T, and then XR. So I have arbitrary family of Calabi-Yau varieties, and from another one, from the first conjecture, I have the universal family. So if I start computing the Hasse-Witt invariant from for the universal family, so the idea is that this is a polynomial of degree p minus 1 in these variables. And how you can compute this polynomial is the procedure which comes from physics. You do the mirror map, then you compute these rational functions, you multiply it with holomorphic period to the p minus 1, you insert the mirror map, and then you'll get integer coefficient, you do mod p, and then you try to find this. Anyway, let me do the last thing, and I finish it. So there are a lot of details missing. Huh? S? No. This is the dimension. No, this okay. This is the m-dimensional. But the point that S is a moduli space. There are coordinate T1 until Tm, but there are polynomial relation. At the end, the dimension of S is m plus 1. But there are many more variables defining it. In general, in our examples, they are the same. M plus 1 is this S. But in general, it might happen that you need more variables, but in order to reach the correct dimension of m plus 1, you must have a lot of polynomial relation. But maybe I put the last things and then finish it. So maybe in order to be sure that everything is, for example, maybe I put this. For example, in the case of elliptic curves, X the Legendre family. Then one can compute a lot of things. For example, then the Z, Q, if you insert the mirror map, it becomes theta 2 to the 4, theta 3 to the 4, you can compute it. It becomes something like 16q minus, you can put as much as you want. And then once you compute, for example, this returning back to the issue of T2 and T3. The TQ ZQ plus 1. So in the case of elliptic curve, these integrals are hypergeometric functions. So for at the end you get 1/2, 1/2, 1/2. This is the Gauss hypergeometric function, ZQ. So this expression, once you insert the mirror map, actually you will have the Eisenstein series E4, but because of some reason it is E4 evaluated at Q2. And there's the same some Z Q to the 3 minus 3 ZQ plus 1. The same, actually here there is 4. And then the same things to the 6, E6 to the. Anyway, soon we will write the article, but hypergeometric series, so when you repeat the same algorithm that I didn't explain so much for this family of elliptic curve, you compute a mirror map, there is a way to say that what is exactly these two polynomials in C. Period to the 4, period to the 6, then when you put the mirror map, then you will get a Eisenstein series E4 and E6, and and etc. etc. So the moral of the story that you can this aspect of elliptic curve can be generalized to modular forms, but the point is that everything is still in the level of conjecture. Why? Because once you take a family of Calabi-Yau variety, first of all, we are talking about Q series, and we have identities, but we just check the coefficients for, let's say, 100 coefficient, 200 coefficient, and we have prime also, and we check it for first 100 primes. So, and for this reason, all these things that I read at the end, it is in general, they are in the level of conjecture. Actually, a lot of the statements in the Calabi-Yau n-fold, they are in the level of conjecture because the people just compute it for examples of Calabi-Yau varieties, and at the end, they are not interested to prove for arbitrary Calabi-Yau variety. But anyway, okay, so I finished.